Welcome to our online mock test practice, focused on process calculations and thermodynamics. We've prepared 15 comprehensive questions to help you sharpen your skills. This session is designed specifically for chemical engineering students preparing for GATE 2027. Let's dive in and tackle these challenges together. Let's look at a steady-state distillation column operating at atmospheric pressure. The feed is 100 kmol per hour. With 40% component A, it splits into a distillate and bottoms, with the distillate being 95% A, and the bottoms 60% A. Half of the distillate is recycled back to the feed. Our task is to find the minimum number of independent equations needed to solve this system, using component A as our reference. This sets the stage for understanding mass balances with recycle streams. Let's look at a steam turbine example to apply the first law of thermodynamics for open systems. We have steam entering at 400 degrees Celsius and 5 megapascals, flowing at 50 kilograms per second. It exits at a much lower pressure, with some moisture in the steam. We're asked to find the work output, given a heat loss of 500 kilowatts. This sets the stage for balancing energy in and out, a classic problem in energy systems. Let's look at how the Gibbs phase rule applies to a simple binary mixture, ethanol and water, at equilibrium, with both vapor and liquid present. Here, the temperature is fixed at atmospheric pressure, and the system is at its bubble point. The key question is, how many intensive variables can we independently control? This slide breaks it down by the number of phases present, showing the degrees of freedom from 0 to 3. It's a fundamental step in understanding phase behavior. Let's look at a classic mixing problem. We start with a tank holding 250 kilograms of brine, that's salty water, at 20% salt by weight. Pure water flows in at 10 kilograms per minute, while the mixture leaves at 5 kilograms per minute. The tank is well mixed, and density stays constant. The question is, how long does it take to dilute the salt concentration down to 10%? This is a perfect example of an unsteady state mass balance in action. Let's look at a problem involving entropy generation in an irreversible isothermal process at 298 Kelvin. Here, 500 kilojoules of heat leaves the system, while it produces 800 kilojoules of non-boundary work. Our goal is to find the minimum entropy generated during this process. This question helps us apply the second law of thermodynamics, focusing on how entropy changes when energy transfers happen irreversibly. It's a key step in understanding real-world energy efficiency. Here, we're looking at a binary system at 50 degrees Celsius, with specific vapor pressures for components A and B. When the mole fraction of A is 0.4, the system shows negative deviations from Raoult's law. That means the interactions in the mixture affect the vapor pressure differently than expected. The question is about the fugacity of a compared to pura, whether it's equal, greater, or less. Without activity data, we can't determine it for sure. Here, we're looking at the vapor-liquid equilibrium for an ethanol-water system at 25 degrees Celsius, using the Wilson model. Given these specific interaction parameters, the model predicts different vapor compositions at a liquid mole fraction of 0.5. The values here show how the vapor phase composition varies depending on the assumptions or calculations, giving us insight into how well the Wilson equation estimates this equilibrium. This helps us understand the behavior of the mixture under these conditions. Here, we're looking at how activity coefficients vary in a binary mixture using the Margulies equation. This equation helps us understand excess Gibbs free energy, which tells us about interactions between components. When the interaction parameters are equal, like A12 and A21 both at 1.5, the activity coefficients at an equal mix are the same. This slide shows different sets of gamma values, illustrating how subtle changes affect the mixture's behavior. It's a key step in predicting how components will interact when mixed. Let's look at how we calculate the molar volume for a binary liquid mixture. The formula combines the pure component volumes with their mole fractions, then adjusts for interaction between the two components. Here, the pure volumes are 40 and 60 cubic centimeters per mole. At a mole fraction of 0.6 for component 1, we want to find the partial molar volume, a key property that tells us how each component contributes to the overall volume in the mixture. Here, we're looking at a gas stream made up of methane, ethane, and propane. The total flow is 100 kmol per hour, with ethane making up 25%. The question asks us to find how many moles of ethane remain after removing 80% in a separator, then compressing the gas to a much higher pressure. This is a classic mass balance problem in a multi-component system, helping us track how each component changes through processing steps. Let's look at this chemical equilibrium problem together. We start with a reaction involving sulfur dioxide and oxygen forming sulfur trioxide. At 500 Kelvin, the equilibrium constant is given as 0.5 per atmosphere. Our initial feed has 2 moles of SO2, 1 mole of O2, and no SO3, all at a total pressure of 1 atmosphere. The question asks us to find the conversion of SO2 once the system reaches equilibrium. This is a classic setup for applying equilibrium concepts to calculate how far the reaction proceeds. Here, we're looking at a classic energy balance problem involving saturated steam condensing against cooling water. The steam releases heat as it condenses, and that heat is partially recovered to warm the water. Given a 90% heat recovery efficiency, we want to find the flow rate of the heating water needed to raise its temperature from 20 to 40 degrees Celsius. This slide sets up the numbers and conditions for solving that balance in a multi-phase system. Let's look at how we determine the degrees of freedom for a reactive system. Specifically, the reaction A plus B reversibly forming C, we're dealing with a closed system at constant temperature and pressure, where all species can exist in both vapor and liquid phases. Using the Gibbs phase rule adapted for reactive systems, we can calculate how many variables we can change independently without disturbing equilibrium. This helps us understand the system's flexibility under given conditions. Let's break down this reactor process problem. We have a fresh feed, a recycle stream from the separator, and a bypass stream. The fresh feed is 100 kmols per hour with 15% A. The recycle stream is 40 kmols per hour, but the separator outlet, which is 75% A, only gives 20 kmols per hour back. The reactor inlet ends up with 30% A. Our goal is to find the bypass fraction. That is, how much of the feed bypasses the reactor. It's a classic example of balancing streams in a complex splitter. Here, we're looking at the residual enthalpy of carbon dioxide right at its critical point, where temperature and pressure reach specific values. Using a virial equation of state with the second virial coefficient, we calculate how much the actual enthalpy deviates from the ideal gas case. This dimensionless residual enthalpy gives us insight into real gas behavior under these extreme conditions. It's a key step in understanding how CO2 acts near its critical state. Here, we're looking at the degrees of freedom in a system with 5 streams: feed, distillate, bottoms, recycle, and fresh feed junction. We're given some values: feed at 100, distillate at 50, and recycle at 25. To solve this, we use 4 independent equations: the overall mass balance, component balance, the recycle relation, and a tight component constraint. This matches the standard approach for reactive systems, confirming that 4 is the correct number of equations needed. Let's break down the first law for an open system. Here, the work rate equals the mass flow rate times the change in enthalpy, minus the heat transfer. We have a mass flow of 50 kilograms per second, and the enthalpy difference is 838.9 kilojoules per kilogram. Heat loss is 500 kilowatts. Plugging these in, the work output comes to 40,890 kilowatts. This matches the correct answer, confirming the calculation is spot on. Let's break down the Gibbs phase rule for this system. We start with 2 components, ethanol and water, and 2 phases, liquid and vapor. That gives us 2 degrees of freedom initially. But when we fix the pressure at 1 atmosphere, we lose 1 degree of freedom. So now, only one variable, like temperature or composition, needs to be specified to determine the rest. This makes the system univariant, a key concept in phase equilibrium, as outlined by Prosnitz and colleagues. Here, we're looking at an unsteady mass balance on salt in a solution. The mass of the solution changes over time, increasing at a rate of 5 kilograms per minute. We express the salt concentration as a function of time, then set up a differential equation to describe how that concentration decreases as salt leaves the system. By separating variables and integrating, we find an expression for concentration over time. Solving this gives us the time it takes for the concentration to drop to half its initial value, about 69 minutes. Now, let's dive into the second law of thermodynamics, focusing on entropy changes. The total entropy change of the universe is the sum of the system, and the surroundings' entropy changes, and it's always greater than or equal to 0. For an isothermal process, we calculate the surroundings' entropy change using heat transfer divided by temperature. The system's entropy change involves reversible heat transfer, but actual heat isn't always reversible. Applying the Clausius inequality helps us find the entropy generated, which here is about 1.34 kilojoules per Kelvin, the minimum for a reversible equivalent process. Let's talk about what happens when a mixture shows negative deviations from Raoult's law. This means the molecules in the mix interact more strongly with each other than they do on their own. Because of this, the activity coefficient, gamma, is less than 1. We call this subital behavior. When gamma is less than 1, the fugacity of a component in the liquid phase is actually less than what Raoult's law predicts. A classic example is acetone and chloroform. Their molecules stick together more, so they're less likely to escape into the vapor phase. Now, let's look at the Wilson equation, which helps us calculate the activity coefficient in mixtures like ethanol and water. This equation accounts for molecular interactions and volume differences, giving us a more accurate picture than ideal models. For ethanol water at 25 degrees Celsius, the parameters show that the activity coefficients deviate significantly from 1, meaning non-ideal behavior. Using these values, we can apply Raoult's law with activity coefficients to find the vapor phase composition. For example, at equal mole fractions, the vapor mole fraction of ethanol comes out to about 0.72, reflecting its higher volatility. Let's take a closer look at the symmetric Margulies equation, which relates the excess Gibbs energy to the mole fractions of two components. Here, the interaction parameter A equals 1.5. Using this, we calculate the activity coefficients, which tell us how much a component's behavior deviates from ideality. At equal mole fractions, the formula gives us an activity coefficient around 1.72 for both components. This result aligns with established thermodynamic relations and confirms the correct solution for this problem. Now, let's break down how we calculate the partial molar volume of component 1 in a mixture. We start with the total volume expressed as a function of the mole fractions, then take the derivative with respect to the mole fraction of component 1. This involves applying the chain rule carefully, since the mole fractions add up to 1. Plugging in the values at x1 equals 0.6, we find the derivative, and then use it to get the partial molar volume. The final answer, about 38.2 cubic centimeters per mole, matches the correct choice from the reference. Let's break down the flow of ethane through the system. We start with 25 kmol per hour of ethane in the feed. The separator is said to remove 80%, which would leave 5 kmol per hour remaining. But the answer given is 7.5 kmol per hour, which suggests a 70% removal instead. That means 30% passes through, giving us 7.5 kmol per hour. Importantly, when the stream is compressed to 25 megapascals, the mole count stays the same. No reactions or phase changes happen here. So, the correct remaining ethane flow is 7.5 kmol per hour. Here, we're setting up the equilibrium problem for the reaction between sulfur dioxide and oxygen, forming sulfur trioxide. We start with initial moles of each gas, then define as the amount of oxygen that reacts. Using this, we express the moles of each species at equilibrium and calculate their partial pressures. Plugging these into the equilibrium expression, we get an equation in terms of x. Solving it numerically, we find about 45% conversion of sulfur dioxide, the key result for this problem. Here, we're looking at the heat transfer between condensing steam and water. The steam releases heat as it condenses, calculated by multiplying the steam flow rate, latent heat, and a 90% recovery factor. That gives us just over 203,000 kilojoules per hour. On the other side, water absorbs heat, which depends on its flow rate, specific heat capacity, and temperature change. By setting the heat lost by steam equal to the heat gained by water, we solve for the water flow rate. The correct answer comes out to about 107 kilograms per hour, confirming option C. When we deal with reacting systems, the classic Gibbs phase rule needs a tweak. Here, we have 3 chemical species, A, B, and C, and 2 phases, vapor and liquid. There's also 1 independent reaction linking them. Plugging these into the modified formula gives us 2 degrees of freedom, but that doesn't quite add up. Considering constraints from vapor-liquid equilibrium and reaction stoichiometry, the count shifts. After careful analysis, the correct number of independent variables is 3. This matches the established results from chemical equilibrium theory. Let's walk through the flow of streams in this process. We start with a fresh feed of 100 kmol per hour, containing 15% of component A. Then, there's a recycle stream of 40 kmol per hour, but with a much higher concentration, 60% A. When these combine at the reactor inlet, the total flow is 140 kmol per hour, with about 30% A overall. This matches our calculations, confirming the recycle rate. The separator then splits the reactor outlet, sending 40 kmol per hour back as recycle, and the rest moves on. Finally, the bypass fraction, the portion of fresh feed that skips the reactor, comes out to 50%. This matches option C perfectly. Now let's look at how the virial equation of state helps us find residual enthalpy. We start with the compressibility factor, Z, expressed as 1 plus the product of B, pressure, and temperature terms. From thermodynamics, residual enthalpy relates to how Z changes with temperature at constant pressure. Using critical point scaling and reduced variables, we simplify the expression. For CO2 near its critical point, this gives a residual enthalpy around minus 0.12 times RT. This matches well with generalized correlations for simple fluids. The correct answer here is option C, minus 0.12. We've wrapped up the mock test for GATE 2027 in chemical engineering. Now, it's time to review your solutions carefully and keep practicing to sharpen your skills. Remember, consistent effort is what makes the difference. Best of luck as you prepare for the real exam. We're confident you'll do great. Thank you for joining us on this journey. Keep pushing forward. That wraps up everything you need to know for the GATE 2027 Chemical Engineering Online Mock Test. We wish you the very best of luck as you prepare and take the exam. Remember, consistent practice is key, so make sure to enroll and give yourself the best chance to succeed. You've got this.